Hi, I'm Jamie with Chegg Tutors. Today I want to talk to you about complex numbers, which actually aren't that complex. They just got that name and kept that name from tradition. The fundamental thing about complex numbers is that they were invented as a solution to an algebraic problem, and they revolve around this number we call I, which we define as the square root of -1. This opens up a whole new world, because negative numbers didn't used to have square roots at all. Now where this comes from is that the algebraic equation x squared plus 1 equals 0, if we just use real numbers, has no solution. If we use the quadratic formula, we get a square root of -1 term, and that's it, we can't solve anything. Now people wanted to make algebra a lot neater, and they said, well, let's invent a solution and see where it gets us. They define this number I as the square root of -1. Now this equation has a solution. Not only that, but any algebraic equation like x to the n plus something times x to the n minus 1 all the way plus a constant, any polynomial like that of degree n, if you set it equal to 0, it has n solutions exactly. Adding the number I makes math a lot more elegant. It also makes things like electrical engineering, vectors in physics, or geometry proofs much easier once you get the hang of it. Let's take a look at two different ways to represent complex numbers. Here's the first one that's really common. You have a complex number, you could just say it's a real number, say a, any real number, plus another real number, b, times I. So you break it up into components. It's a real number plus what we call an imaginary number, something times I. And that is an algebraic way of looking at things. We have two real numbers, it's an expression. We can do things like multiplication, just like we do them when we're multiplying algebraic expressions, just keeping in mind that I squared is -1, which means I to the third power is -I, because exponents work just like they do for regular numbers that you're used to. And I to the fourth power is 1. So we do multiplication the same way. You just multiply terms like you would expand a binomial. You can use FOIL or whatever other method you want, except keeping in mind the basic definition of I. Now there's another way we can look at complex numbers that's actually quite elegant and gets us very far in both physics and in math. We take this number, a plus bi, and we put it on a grid. It's almost like we've now created a two-dimensional number. One dimension is real, and one dimension is what we call imaginary, even though it's very much in existence too. Here, we take the x-coordinate to be a, and the y-coordinate to be b, and here we call this the imaginary axis instead of the y-axis, and our complex number becomes just a vector in the two-dimensional plane, with x-coordinate a and y-coordinate b. I'll show you another way to look at this that doesn't use this algebraic formulation as much, but makes multiplication much easier and shows us the geometry of complex numbers. And that way is to treat this number that we formed from a plus bi in the coordinate plane like any other vector. It has a magnitude, r, the length of this vector, and it has an angle, theta, the angle from the positive x-axis. So if we are to convert between the a plus bi algebraic version, which is helpful in algebra, to something that's more helpful in geometry or physics or electrical engineering, we change this a plus bi representation and write it in terms of vectors. Now if you're familiar with the unit circle, this will look very familiar, but nonetheless, I'm not going to worry about how we derive it. We can also write a plus bi, it's equivalent to r, the real number r, which is the length, times the cosine of theta, plus I times the sine of theta. Don't worry too much about how to derive this. You can look up the unit circle and figure it out. But once we have this representation, a lot of useful things follow. I'll just show you one of them. If we multiply a complex number by I, that's the same as changing bi to -b and a to ai. That is exactly the same as rotating by 90 degrees in the vector circle. We can see that most easily if we were to take a number a and multiply it, just a real number a, multiply it by I. A starts out on this x-axis, it ends up rotated 90 degrees all the way to a purely imaginary number on the y, or imaginary axis. So if we multiply by I, it's rotation by 90 degrees. If we multiply by a real number, as you can tell, we're not changing the theta value, we're only changing the value of the length. So this becomes, instead of a vector of length r, a vector in the same direction of length c times r. What this means, and this is really crucial, is that we can think of complex number arithmetic or algebra as a geometry where complex numbers are vectors, and multiplication by complex numbers is simply a rotation and a scaling. This becomes really important when both in connecting algebra to the calculus of complex functions, which is useful in all kinds of areas. I hope you'll continue working with complex numbers, and I hope this made it a little easier. See you next time.